Everyone, welcome back for another edition of No Here, No Problem. Today we're going to be working on Unit 8, Section 5, which is talking about accounting principles. So in this section, we're going to be talking about the fundamental accounting principle. Oh, geez. We're going to be talking about fundamental accounting principle, um, permutations, distinguishable permutations, and then combinations, and then some problems that kind of mix it all up, all right? This section, every single question in this section is a pretty quick question to actually solve. It's setting it up that is going to take a little bit of time. So, the discussion here is going to take longer than the actual problem itself for most of these, okay? Um, in honor of the Bears here firing Matt Eberflus, I went ahead and decided to wear a Bears hat. Excited about that decision, seeing as he's not been doing a good job. But, anyways, back to math. All right. So let's get started here. So in this section, at the end of this, I went ahead and I posted help on questions 12 through 15. So feel free to jump ahead to that portion of it if you would like, but I just went ahead and created some problems just like 12 through 15 that are from the homework on WebAssign, similar to them to kind of guide you a little bit. All right, so let's get started here. So we have many different ways of doing counting principles, and there's some that are really simple and some that get very complicated. So when we have very simple counting problems, such as, I'll give an example here. You place 8 pieces of paper that are numbered from 1 through 8 in a box. You're going to draw one of those pieces of paper at random from the box. You record the number. You're going to put the paper back into the box. And then you're going to draw a second piece of paper at random from the box and record its number. So then you're going to take these papers, which you took out, and you're going to go ahead and add them together. And then you're going to determine how many ways you can get where the two papers add together to give you a sum of 12. So let's try to imagine what this actually looks like, and some restrictions are on this problem. If I was to pick first a 1, a 2, or a 3, so let's say I reach in the box, I pick a 1, a 2, or a 3 out of the box. In order to get them to add up to 12, I would need to pick an 11, a 10, or a 9 so that they actually do add up to 12, right? 1 plus 11, 2 plus 10, 3 plus 9. It's not possible. My box is only numbered, or my pieces of paper are only numbered from 1 to 8. I don't have a 9, 10, or 11. So this scenario, we can go ahead and take it off the table. It's just not possible. So then let's imagine the other scenarios. If I was to pick a 4, a 5, a 6, a 7, or an 8. So let's say on my first pick, I go ahead and pick out a 4, a 5, a 6, a 7, or an 8. In order to get it to add to 12, and I put the paper back, my second paper would have to be then an 8, a 7, a 6, a 5, or a 4. So these are the possibilities. There are 1, 2, 3, 4, 5 different ways that I can get this. Now you'll notice that this right here, these two are exactly the same, and these two are exactly the same. Because I could pick a 5, and then I could put it back and pick a 7, or I could pick a 7 first and then pick a 5. And so these are just listing the different ways, right? In this case, the order itself does not matter. A 5 and a 7 and a 7 and 5 are considered two different draws. So when we look at this, there's 5 different ways that I actually draw two pieces of paper that will add up to a total of 12, okay? All right, so when we get into more complicated counting principles, we use a process called the fundamental counting principle. So in a fundamental accounting principle, what it says is basically, to summarize this statement that's right here, is that if I have 2 events, or 3, or 4, or 5, or so on and so forth, the number of ways that the first event could take place and the number of ways a second event could take place just get multiplied together. So let's say, for example, I'm going to make a sandwich at Subway. I'm going to do 3 kinds of bread, and I got 4 kinds of meat. Okay, or I could say bread and cheese and meat. So those are multiple events that are taking place. The different sandwiches you can make. This is why they say there's millions of opportunities for sandwiches at Subway. That's because somebody can go ahead and pick cheese. Somebody can pick no cheese. Somebody can pick turkey. Some pick ham. Some can pick ham and turkey. So this is a more advanced method of counting principle. Well, when we're doing this, think about it something simple as this, right? How many different pairs of letters for the English alphabet are possible? Well, when we look at the alphabet, there's 26 letters, right? In the English alphabet, there's 26 letters. If I go ahead and I'm going to choose a pair, that means I've got 26 to pick from. And then for my next event, I've got another 26 to pick from. So it's as simple as just simply saying 26 times 26, okay? So when we look at this, there's 676. Now, what if I wanted to modify it? Let's say I was going to do a letter and then a number. Well, if I did a letter, there's 26 letters. But then let's say I was going to pick a number from 0 to 9. Well, from 0 to 9, there's numbers. There are 10 of them. So there would be 260 ways I could do this. So I could do A1, A2, A3, A4, A5, B1, B2, B3, and there would be 260 different ways that I could do this. This is the fundamental counting principle, okay? So one important application for the fundamental counting principle is the idea of a permutation, which means that we are doing a situation where the order of events takes place. And so an example is like in a horse race. A horse race, the horses come in and they come in first, second, and third place, right? You can't change that. First place, let's say the three people are racing or three horses are racing and you've got Doug, John, and Eric, okay? Doug comes in first, John comes in second, Eric comes in third. That order is very different than if like Eric came in first, Doug came in second, John came in third. So the order in that case matters. So therefore we call this a permutation. So if we were to say, how many different ways can I arrange the letters A, B, C, D, E, F? Okay, when we say how many permutations, we're saying how many ways can I order these letters? So if you think about what's happening here, we've got 6 different letters going on, right? We got letter 1, 2, 3, 4, 5, 6. We have 6 different letters going on here. I'm going to go ahead and just pick one of these letters. So let's say I pick a B. I have 6 letters I could draw from. There's a total of 6 letters here, right? But I'm going to pick one of those to go into that first spot. So we're going to go from the 6 letters have the possibility of going in that first spot. I take that one off the table. So 6 people are racing, only one of them can come in first, but of those 6, there's 6 people that can come in that first spot. Okay. I take that person off the table. They've crossed the finish line. Now there's 5 more remaining. I go and let's say E. All right. From here, now there's only 4 more remaining. And then there's 3. And then there's 2. And then there's 1. And in this case, any of the 6 letters could be in that first position. Once I've used it, any of the 5 remaining can go in the next position. Any of the 4, any of the 3, any of the 2, any of the 1. And what we're looking at here is basically a shorthand way of saying 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So when we're talking about permutations in an event, we simply can say n factorial, which is 6 factorial. And when we're talking about permutations in the extended form, we could say it's 6, and we're choosing 6 in this case. But the formula is n factorial divided by n minus r factorial. So, for example, if we were to go ahead and say, in this case, let's modify it. We're going to, instead of using all 6, let's say in this example, we're talking about there's 8 horses, as the example I gave earlier. So there are 8 horses, and we're going to talk about the first 3 positions. And this is a permutation because the order matters. So we have 8, we're going to pick 3. And when we say this, think about exactly what's happening here, right? We have 8 horses that are racing. 8 of them can come in first place. After one of them is crossed, there's only 7 remaining. After 2 of them have crossed, there's only 6 remaining. But there's first, oh, that's a terrible, terrible number. First, second, third place, right? The order matters here. So what does this look like if you were to do just permutations? Well, we would say NPR, which is 8 pick 3. The formula is going to be 8 factorial divided by 8 minus 3 factorial. If we go ahead and simplify this, we have 8 factorial divided by 5 factorial. And what's going to happen is that 8 factorial is going to break down into 8 times 7 times 6 times 5 factorial. Your 5 factorials will cancel out, leaving you with 336. But you'll notice that the same thing here is what's going on here. So permutations and fundamental counting principle work out to be exactly the same. It's just permutations is more of a formula. Okay? All right, let's go ahead and look at permutations when we're talking about distinguishable permutations. What this formula says is that we look at the number of objects that are taking place and we break them down into their individual parts. So this is the first event, this is the second event, this is the third event, so on and so forth, depending on how many there are. So, for example, when we're talking about distinguishable permutations, if I was to say, in how many distinguishable ways can the letters in the word banana be written? I'll show you what I mean by distinguishable. If I go ahead and rewrite this as BNNAAA, you could tell that I've rearranged the letters, right? That's a distinguishable permutation. I've rearranged it. You can actually see it. I'm going to go ahead and for the second example, I'm going to rearrange it. You ready? BANANA. All right. What I did was I distinguished it. I actually switched letters. You should see it, right? I switched these two letters. You can't. It's not distinguishable. I can't see that I actually rearranged it. And so we say that this is a non-distinguishable rearrangement, and we want to know the distinguishable rearrangement. So how do we do this? Well, when we look at this, we break down the letters and how many there actually are. So when we look at this, in the word banana, banana has 6 letters. Okay, there's a total of 6 letters. As far as the A's go, there are 3. As far as the N's go, there are 2. And as far as the B's go, there's only 1. So these are each of the individual events, excuse me. So to break this down then, using that formula we just said, we have n factorial divided by n1 factorial, n2 factorial, n3 factorial, and we have 6 for the total number. We have 3 for the letter A, we have 2 for the letter B, I'm sorry, N, and then we have 1 for the letter B. Just go through and simplify this in the calculator, and we end up with an answer of 60. The thing to note that's very important is make sure that this is all in one fraction. Your calculator has this tendency to take stuff and go like 6, and if you were to do divided by, it would actually write it like this. It would say divided by 3 factorial times 2 factorial times 1 factorial. And your calculator is not good with fractions unless you specify a fraction. If it looks like this, it's not going to understand that it's actually taken and doing division by that 3, 2, 1 on the bottom. It thinks it's doing 6 divided by 3, getting that answer, and then multiplied all by 2 times 1 factorial. All right. So these are the actual distinguishable permutations. You can see that these are the actual 60 permutations. All right. Again, if I was to rearrange these 2 A's right here, you wouldn't be able to tell, so it's not considered a distinguishable permutation. All right, let's continue on. So now let's talk about where the order doesn't matter, where we're talking about a combination. Combinations have this formula. We actually did when we did the binomial expansion. This is the formula you use when we're talking about combinations. And when we mean a combination, we're saying the order doesn't matter. So if I was to give you the letters A, B, and C, that's the same thing as giving me a BAC, a BCA, a CAB, a CBA. Those are all exactly the same, so we don't count them again because the order didn't matter. It's the same thing. So when we do combinations, we should get numbers that are vastly smaller than permutations because we're eliminating the redundancies that take place. I'll give you an example. So for a combination, it says, in how many different ways can 3 letters be chosen from A, B, C, D, E? The order of the 3 letters is not important. Remember that A, B, and C is the same as C, B, and A. So in order to set this up then, it's as simple as saying we're going to have 5 letters. We're going to choose 3 of those letters. Throw into your formula, throw into your calculator, simplify it, and we should get that there's only 10 ways that we can actually do this. Okay? Just like when we talk about a standard deck of cards, there's 52 cards in a deck of cards. And if I was to go ahead and play a game of poker, I'm giving you 5 cards. Now, I could rearrange the cards in my hand, but no matter what, I'm giving you 5 cards. So like we did this in class the other day, that an ace 2, 3, 4, 5 is the same as a 5, 4, 3, 2, 1 because it's the same exact hand. I could rearrange it however I want. So if we have 52 cards, I'm going to give you 5 cards. So go ahead and simplify this using all your different steps that you would use to break this down. We end up with 2,598,960,000 hands. This is how many different hands you can get in a standard game of poker if you were dealt 5 cards right out of the gate. So when everybody's like, oh, I got this exact same hand, 2 minutes ago, did you? Because there's 2.6 million different hands that you can actually start with. Okay. They may look similar, but they're not usually exactly the same. So that's all the combinations, permutations, all that stuff. Let's see them in action. All right. So in the homework itself, everything up to number 12 is pretty straightforward standard. 12, 13, 14, 15 are a little bit more challenging. So let's take a look at number 12. Okay, I'm going to talk about, in terms of, the homework talks about Powerball. I'm going to talk about the Mega Millions. So Mega Millions, as of recent history, is generating these massive, huge lottery pots because the probability of winning is so incredibly low. The Mega Millions has a container, which we'll go ahead and call this container over here. Okay, there's the container 1. And inside this container, there are 70 ping pong balls that are bouncing around, numbered from 1 to 70. From this container, a ball is going to come out, and then another ball, and another ball, and another ball. 5 balls are going to come out of this machine. Now, the order doesn't matter because a 1, 2, 3, 4, 5 is the same as a 5, 4, 3, 2, 1 when they come out, just that they're in a different order originally, but the order itself doesn't matter. So that's a combination because order doesn't matter. So we have white balls, we have 70, we're going to choose 5 of them. When we look at the gold balls, there's a separate container. So this is container 2. There's a separate container altogether. This container has only gold balls, and we're going to pick just one of those special power balls. And so we have 25, we're going to go ahead and choose 1. Now this is a fundamental counting principle problem because there's multiple events taking place, right? We have event 1, which is the white one's taking place. Then we have event 2, which is the gold one taking place. We're going to multiply these together because of fundamental counting principle, and we end up with 302 million different draws for the Mega Millions. This is why people are not winning this, and this is why the pots are getting so big, because your odds of winning 302 million are terrible. If I do one pick, I've got a 1 out of 302 million. So I'm more likely to get struck by lightning twice. Okay. All right. When we look at forming a committee, this is again a fundamental counting principle, but there are restrictions going on here. So when we look at this problem, there's 6-member research team is going to be formed. So we're going to have 6 total people involved in this. Okay. From this team, there's going to be administrators, there's going to be faculty members, there's going to be students. All right. Now, when we look at just the admin, we are told that there's only going to be 1 admin picked, but there are 7 admin to choose from. So we're going to do 7 admin. We're going to choose just one of those. So that means we have 7 total admin we could choose from. Obviously, that makes sense, right? We only have 1 that we could pick. When we look at the faculty, there's going to be 3 faculty members we're going to pick, but there's 12 to pick from. So we're going to do 12, choose 3. And from this, we put this in, we're going to get that there's 220 different ways that I could choose those 3 different faculty members, right? John, Bob, and Dave are the same as Dave, Bob, and John. Same exact 3. The order didn't matter there, okay? The last thing is the students. There's 25 students to pick from. I'm going to pick 2 of the students. So 2 students, that means that we're going to have 25, and we're going to pick 2. So then this means we have 300. There's multiple events taking place, but it's all condensed into 1, really. So we have to do fundamental counting principle, multiply these together. We have 462,000 different types of committees, 6-member committees that I can actually choose. Okay. All right, take a look at number 14. This one is a tough one. This one's a little bit of a doozy, so I have to really explain this, okay? A shipment of 40 smartphones contains 5 defective phones. So in how many ways can a store select 6 of these smartphones and receive the following? All non-defective, meaning we're going to choose 6. For A, B, and C, we are choosing 6 phones, all right? But these are different scenarios. So we have to first break this down. We have 40 phones. 35 of them are good. Only 5 of them are bad. So when it says for part A, all of the non-defective phones are being picked. That means we're going to choose 6 phones, but from our 40 phones, only 35 of them are good. So we have 35 phones that are good. We're going to choose 6 of them. Okay, so there's only 1,600,000 only 1,623,000 different ways that I can choose 6 phones from the 35 that are good. Okay. For part B, 4 non-defective phones, meaning 4 that are working. Okay. And so when we look at this, the first one is that if we say there's 4, but we're choosing a total of 6, right? We're choosing 6. There's 4 good ones that we're going to pick. That means that 2 of them are going to be defective, right? So we have different events going on here. We got 4 and we've got 2. Let's go ahead and write out the scenarios for 4 and write out the scenario for 2, excuse me. So for there being 4 good, we have 35 phones that we could choose from, right? That are good, 35 that are good. And we're going to choose 4 of those. All right. So think about what the next one would be. Now we're going to talk about there's 4 good, there's going to be 2 bad. Well, how many bad are there? There are 5 bad. And we're going to choose 2 of those bad. So it's 5, and we're going to choose 2. Some fundamental counting principle going on here. We're going to go ahead and say that we have 52,360 times 10. So there's going to be a total of 523,600 that I can choose where there's 4 good and there's 2 bad. Okay. Now we've got a scenario where we say at least 5 non-defective. So this is one where instead of multiplying, because it's not just going to be one scenario where there's going to be like 5 that are not defective, because it says at least 5 non-defective, we've got multiple scenarios now. And because of that, when we have multiple scenarios, we don't multiply them, we actually add them together. So when I say at least 5 non-defective, we're saying first there could be 5 that are not defective. That's one scenario. The other option is when we say that there are 6 that are not defective. Okay? If this had been saying at least 4 that are not defective, we'd have to do 4 and 2, 5 and 1, 6 and none. Okay? But in this case, we're saying at least 5 that are not defective. So what does this look like? Well, in the first scenario, we have 35 phones. We're going to choose 6 of them, and all of them are going to be good. Okay? In the second scenario, we're going to go ahead and choose from 35 phones, 5 of them are going to be good, okay? And then 1 of them is going to be bad. So 1 is going to be bad. We're going to do 5, choose 1. Now, in this scenario, this is another pick right here. This is a scenario of a pick. This is one event, right? And then this is another event, and we're going to be adding these together, okay? So just throw these into your calculator. We get 1,623,000. In the other one, we get 1.5 million. There's a total of 3,246,320 different ways that I can actually have those smartphones from that pile. Big number, but this is a setup here, okay? All right. And the last question, it looks confusing. It really does, but it's really supposed to be super simple to work through this, okay? You have to recall first that when we're talking about solving for n here, that in the formula NPR, we know that the formula is n factorial divided by n minus r factorial. So when we look at this, they're giving me this, that this is my n and that this is my r, right? So we're going to put those values into our formula. On the left side, here's what that would look like. I put in, for my n value on the top, I'm going to put in n plus 1, because that's what we have right here, okay? For the bottom, we're going to put in n minus r, because we have n and r here. So this is n and r, and if I subtract those, this is what we end up with down on the bottom there. And if I take that and start working through it, you'll see that we have this in its factorial form. Okay, whoops, I just deleted some stuff there. Okay, we have this in its factorial form. If we do the same thing to the right side, what we're going to have is a 4 that gets carried through. But we're going to have this is my n and this is my r. So we'll set this up in our formula. We end up with n factorial divided by n minus 2 factorial. We go ahead and reduce the top so it meets up with the bottom. And then what you're going to see here is that things are going to simplify. These n minus 2's are going to cancel. These n minus 2's are going to cancel. And that's going to go ahead and leave me with n plus 1 times n minus 1. And then 4 times n minus 1. If I divide both sides by n and n minus 1. I can divide both sides by those values because they're the same on both sides. Effectively, I can go ahead and just cancel this out with these 2 over here. So that's going to leave me with n plus 1 is equal to 4, which means that n is equal to 3. Okay? So as I said, the problems themselves are pretty quick to work through this for this entire section. It's just understanding the actual setup. Okay, trial and error sometimes works best until you get the hang of it. But if you have any questions, feel free to ask. Okay, just remember, combination order does not matter. Permutation order does matter. Okay, that's it. You guys take care. Be safe. Don't forget to like and subscribe, and have a great day. Okay.